Hi, welcome to Graph, Homomorphisms and Universal Algebra video session number 3. Today's course is about cores and polymorphisms. In session 2, we have introduced the arc consistency procedure, which is a very nice algorithm both from a practical perspective and from a theoretical perspective. From the theoretical perspective, what is nice is that we fully understand the power of the arc consistency procedure. We understand when this method can be used to solve a constraint satisfaction problem for a given digraph. And the key concept here was the notion of a power graph, and we proved some nice theorems linking the power graph with the arc consistency procedure. Today we'll see two more tools to study the computational complexity of constraint satisfaction problems. It's the concept of a core of a given digraph and the concept of a polymorphism of a given digraph. And in particular, the second concept is the key to translate our problems into universal algebra. So it's absolutely central to this course. Okay, so let's get started. Let's have a look at the following graph, G. If you want to study the computational complexity of CSP of G, very often the following observation can be useful. Suppose that G is homomorphically equivalent to H. Then CSP of G equals CSP of H. The reason is that if there is some graph G prime that homomorphically maps to G, then G prime also homomorphically maps to H. And in the other direction, if H prime homomorphically maps to H, then H prime also homomorphically maps to G. So they're really the same. In our example, you might already guess a graph which is familiar to you and homomorphically equivalent to G and simpler. How do we map H, which is a black triangle in this picture, to G, which contains a red triangle? Well, we simply map the black triangle to the red triangle. In the opposite direction, it's more interesting. We start by mapping the red triangle into the black triangle, and now we have to extend this map to the other vertices of G. And it's easy to see that we can do that here. We fold the other triangle in G, also to the red triangle. We fold this tree, which hangs out the red triangle, to the black triangle, for instance, as follows. And that's a homomorphism. What do we learn from this? Well, we already know CSP of H. CSP of H is, in our example for this graph H, it's the 3-colorability problem, which is well known to be NP complete. So, consequence, CSP of G is also NP complete. If we are given a graph G, how do we find a graph H that is homomorphically equivalent to G and simpler? Well, one way is to look for homomorphisms from G to a proper subgraph of G. In the example here on the right, for example, we can homomorphically map the entire graph to its subgraph, which is the triangle on the top. How do we do it? We fold the lower triangle to the upper triangle and fix the upper triangle. Homomorphisms from G to G seem to be important, so they deserve a name. They are called endomorphisms. You might have already encountered something related, namely isomorphisms between G and G. They are called automorphisms. So automorphisms are special endomorphisms. If our digraph G is finite, and here it's really important that G is finite, the following are equivalent. H is an injective endomorphism, and so the following are equivalent. H is an injective endomorphism and H is an automorphism. It's an easy exercise. So why do I tell you this? Now, suppose our graph G is such that this method of finding a smaller graph, a subgraph which is homomorphically equivalent, fails. In the sense that every endomorphism of G is already injective. We cannot, in other words, we cannot shrink G to a graph, a subgraph H, which is homomorphically equivalent. In this case, we call G a core. So here comes the definition, important in a box. G is called a core if all endomorphisms are injective. All endomorphisms of G are injective. One of the first things that we want to prove about cores is that every finite graph is homomorphically equivalent to a core graph, H. That's what's written here. How do we prove that? Well, suppose our graph is not a core, G is not a core, otherwise we are done. So if G is not a core, it has a non-injective endomorphism. So our picture of G is like that. This is G. So we have an endomorphism. I always draw it like that, an endomorphism E, which has an image of smaller size. Then we look at a new subgraph, induced by the image of E. Let's call it H. There are two cases. H is a core, in which case we're done. H is what we want. If H is not a core, well, it again means we have a non-injective endomorphism. So we repeat the game. We again find an endomorphism E prime with a smaller range, and we continue. And now here it's important that the graph G is finite. All graphs are finite, so this iteration must stop at some point, and it must stop by finding a graph H. And of course, since we can compose all these endomorphisms to obtain a new endomorphism, this will provide a core graph for our original graph G. End of proof. The second fact that we prove about cores is that they are unique in the following sense. Suppose H is homomorphically equivalent to G and a core, and H prime as well is homomorphically equivalent to G and H prime is a core. Both satisfy these assumptions, then H and H prime must be isomorphic. This is also the reason why H is called the core, because it's essentially unique up to isomorphism is. So H is the core of G. How do we prove this? Suppose we have here our graph G, and it's homomorphically equivalent to H, and it's also homomorphically equivalent to H prime. Now observe the following. There also exists a homomorphism from H prime composed with the homomorphism from G to H and all the way back. So here we just composed homomorphisms. Hence, the resulting map E is an endomorphism of H prime. Since H prime is a core, E must be injective. This in turn implies that the blue map that just follows the arcs from H prime to H must be injective as well. So there is an injective homomorphism from H to H prime. In very much the same way, but arguing symmetrically, we also obtain an injective homomorphism from H prime to H. And now it's an easy exercise to prove that if this happens for finite graphs, this means that H and H prime must be isomorphic. Oops. H and H prime are isomorphic. End of proof. So we have seen every finite graph is homomorphically equivalent to a core, and the core is unique up to isomorphism. In general, the core will be simpler than the graph we started with, more symmetric. However, one word of warning: it's in general difficult to say how the automorphism group of the core relates to the automorphism group of the structure we started with. So it's difficult to formalize this notion of how is the core simpler. And your deepest group theory will not help you in answering the question how the core automorphism group is related to the automorphism group of the original structure. In fact, one can prove that the question whether a given finite graph is a core is computationally hard. Polymorphism of a given digraph is a homomorphism from a finite direct power of the graph back into the graph. Slowly, a homomorphism from, let's call our graph G, a homomorphism from G to the K to G is called a polymorphism. What does this mean concretely? Suppose we have edges u1, v1, u2, v2, and so on, until uk, vk. We can then apply our map, our homomorphism, let's call it f, to the first points of those edges, to u1 up to uk, and we'll obtain a new vertex u0. Likewise, we can apply f to the endpoints of the edges, v1 up to vk, and we will obtain a new vertex v0. And to be a polymorphism is precisely to require that no matter how we've chosen the edges, indicated by little arcs now here, suppose there are arcs here, u1, v1, u2, v2, and so on. No matter how we've chosen the edges, there must be an edge between u0 and v0. Let's see an example. It's a little bit a boring example. No matter how G looks like, the projections will always be polymorphisms. So what's a projection? It's a map that sends x1 up to xk to xi for some fixed I. This is also called the Eigth projection. The Eigth projection is always a polymorphism, and this is very easy to see from this diagram here. The Eigth projection, suppose here is I. If f is the Eigth projection, then ui equals u0 and vi equals v0. And since we have assumed that there is an edge from ui to vi, there is also an edge from u0 to v0. That's clear. So these are boring polymorphisms. Let's have a look at some more interesting polymorphisms. Suppose our digraph G is the digraph with the vertices 1 up to n, and the edge relation coincides with the order on 1 up to n. So it's actually the graph that we've also called Tn in the course. So recall T3 looks like that. That's T3. All right, this graph has the following interesting polymorphism. It's a map from the vertices of G squared to the vertices of G. So it has arity 2, k equals 2, and it maps a pair xy to the minimum of x and y. Now, why is this a polymorphism? Why is this a polymorphism? In this situation, one can see it as follows. If you increase the arguments of the minimum, the function value will only increase. There's also an important method of producing new polymorphisms from polymorphisms that you already have. Suppose f is a polymorphism of arity k, and suppose g1 up to gk are polymorphisms of arity m. So homomorphisms from g to the m to g. Now we can produce a new map which has arity m, which maps x1 up to xm to the function value of f. But before you apply f, you apply the g's to x1 up to xm. First you do it with g1 and so on, and then you apply gk to x1 up to xm. And then you take all the resulting function values and you apply f to it. Then this new map called composition is also a polymorphism. of arity. In order to convince you that polymorphisms are something useful, I should link it with something that you already know. And in order to prove this link, I need some properties that functions might have. So we have a function from v to the k to v, and such a function is called idempotent. If when we apply f to equal arguments, we'll get back this argument for all x. A function is called commutative if k equals 2 and we have f of xy equals f of y x for all x, y in V. And finally, a map F is called associative, again binary, yeah? Again, F should be binary. So again, k equals 2. And in this, here we, you know this already, yeah? We can re-bracket. If I have f of x, f of y, z, I can change brackets. And I get the same. If I first apply f to f of x, y, and then with f again apply to z. If all of these three properties hold, then f is called a semilattice operation. So I want that f is idempotent, commutative, and associative. You have already seen examples. One example is the minimum operation. It's a binary operation that returns the smaller of the two arguments. If they're equal, it returns this equal element. So it's idempotent, it's certainly commutative, and it's also associative. So here comes the link between polymorphisms and the topic of last time's video session. Last time we were interested in the question whether P of H homomorphically maps to H. Because this happened if and only if the arc consistency procedure solves CSP of H. Now here comes a sufficient condition that implies that P of H homomorphically maps to H that is easier to verify in many situations. Now this is a proposition. If H is a digraph with a semilattice polymorphism, then P of H homomorphically maps to H. We'll not prove this now. We'll instead prove something more general in a second. And to give you an idea, I will first give you a little example, what we can do with semilattice operations. Suppose f is a semilattice operation, a semilattice polymorphism of H. Now we can produce new interesting polymorphisms via composition. We can, for instance, look at f of f of f of f applied to x1, x2, then take the result, combine it with f with x3, and again with f and x4. All right, did I count you right? 1, 2, 3. Maybe we have another one, x5, right? Now it's okay. So this gives me a function g. G is again a polymorphism, that's what we know. And it has a very nice property. G is what I call totally symmetric. This means the following. This means that if x1 up to x5, the arguments, the set of arguments, equals y1, y5, another set of arguments, then g applied to x1 up to x5 equals g applied to y1 up to y5. In other words, the function value of g only depends on the set of arguments, not on their order, not on their multiplicities. And this is quite clear from the properties of idempotency, commutativity, and associativity. We can rebracket, we can shuffle around, we can duplicate arguments, and will not change the function value. So clearly, totally symmetric, I can define it not just for arity 5, but in general. I will talk about totally symmetric operations of arity k. And now I can finally state this more general theorem, which will provide me a characterization, yet another characterization of the situation that P of H homomorphically maps to H. So let H be a finite digraph. Then the following are equivalent. P of H homomorphically maps to H. A property which is nice, it can be checked on a computer, but it's expensive to check it on a computer because P of H has exponential size. So this can be a lot of work. So we are really interested in alternative characterizations. So the second one is now in terms of polymorphisms. It says H has, for every k, a totally symmetric polymorphism of arity k. And the third item allows me to bound the arity k. The bound will come from the proof. H has a totally symmetric polymorphism of arity 2 times the number of vertices of H. That's enough. So note that this will in particular imply the proposition that we've seen earlier, because if we have a semilattice polymorphism, this will imply 2, and 2 will then imply 1. So theorem, this is a theorem, and the theorem implies the proposition. We now want to prove the theorem. And to prove the theorem, well, it's clear that 2 implies 3. 1 implies 2 will be fairly easy. And we'll finally prove 3 implies 1. Suppose G is our homomorphism from P of H to H. That's a homomorphism. And we have to produce the totally symmetric operations of arity k for every k. So how do we define fk of arity k? So fk with k arguments, we define it as naturally g of the set x1 up to xk. So why is fk a polymorphism? We check the definition of polymorphisms. So we have this diagram. We suppose that x1, y1 is an edge, and so on. Xk, yk is an edge in H. And we have to prove that if you apply fk to the x's and fk to the y's, the resulting pair will be an edge. What's the definition of fk? We look at the bag of arguments and apply g to this bag. Yeah? That's the same with y's. With the y's, we have the set of arguments y's, and in order to know what fk is, we apply g to the arguments. Now look at these two bags. When is there an edge in P of H between those bags? Always, right? Because the definition of P of H says for every element in the first bag, there must be an element in the second bag, so that the two elements form an edge, and vice versa. For every element in the second bag, there must be an element in the first bag, so that the two elements form an edge. This is clearly satisfied by the choice of our x's and y's. So in the power set graph, there is an edge between the first bag and the second bag. Now, G is a homomorphism. So this will tell us that there will be an edge from G applied to the x's to G applied to the y's. And this is precisely the definition of fk. So there will be an edge from fk applied to the x's to the fk's applied to the y's. So fk is a polymorphism. This concludes the proof 1 implies 2. So we are left with 3 implies 1. So in this direction, we are given a totally symmetric operation of arity totally symmetric polymorphism of arity 2 times the number of vertices of H. And we have to find homomorphism from the power set graph of H to H. How do we do it? If we are given a non-empty subset of vertices of H, let's call it x1 up to xn, I map it to f of x1, x2, and so on until xn. And then, if I have not yet reached the arity of k, I repeat the last argument. Any argument, I pick the last one many times until I have reached the right arity k. Let's call k the number 2 times number of vertices of H. Yeah, I repeat until I have reached arity k, so that I can apply f. Note the following observations. G is well defined. It doesn't matter in which order I pick, I list the elements x1 up to xn, because f is totally symmetric. What we have to verify is that G is a homomorphism. And this we'll do on the next page. For this proof, it's really nice to work with pictures. How does P of H look like? The vertices are non-empty subsets of elements of vertices of H. We have to show that if there's an edge between two such bags, vertices of P of H, then G will map the two bags to two vertices of H that form an edge in H. What does it mean that there is an edge between these two bags? It means that by the definition of the power set graph, that for every vertex in the first bag, there is an element of the second bag so that the two form an edge. For instance, like this. And vice versa, for every element in the second bag, there is an element in the first bag so that the two form an edge. Maybe like that. We would like to apply the fact that G was defined in terms of Fk and Fk was a polymorphism. To do that, we will rearrange this mess of edges as follows. We will draw them straight. We list all the edges that go across the bags, but we'll draw them like this. At some point we'll also list the blue ones. We'll list them all. Note that this list will necessarily be smaller than 2 times the number of vertices of H. This is the K, the arity of Fk. We would like to apply Fk, so if this list is too short, we just take the last edge that we've listed and reproduce it until we really reach K. We have now a list of K edges, and now I claim that if I apply Fk to the first points of these edges and Fk to the second of those edges, I obtain the same as G applied to the first bag. And this is really by the definition of G and by the fact that Fk is totally symmetric. Note that here in this list, some elements might be repeated several times. For instance, the edges here on the left, they have a common endpoint x. This would amount in our other list to have several times the same endpoint here. But this doesn't matter for Fk. Fk is totally symmetric, so whether you have 2 times x, several times x repeated, doesn't matter. Okay, Fk is a polymorphism. By the polymorphism condition, we obtain that there is an edge between the function value of Fk applied to the starting points and Fk applied to the endpoints, and this in turn means that there is an edge between the function value of G applied to the first bag and the function value of G applied to the second bag. And this proves that G is in fact a homomorphism. End of proof. Alright, so we have proved a very nice theorem. I should illustrate a little bit how useful this is. Suppose we want to understand the CSP of the following graph here. Now this zigzag graph, how difficult is the CSP? Oh, we don't know so many tools. We know arc consistency. So the question is, does arc consistency solve CSP of H for this H? Okay, so what do we know? We know that we have to check it's sufficient and necessary P of H homomorphically maps to H. Oh, but P of H, this will be very large, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. So, power set, this power set graph will be very large. So you don't want to draw it by hand. But what we know is that if H has a semilattice polymorphism, then we have that the power set graph of H homomorphically maps to H. And that's something much easier to check. There are not so many binary maps on a set with 9 elements. Yeah, that one can try, and that's actually a good exercise. Find one. Now we have seen that for the tournament graph, the minimum operation was semilattice polymorphism. Now here, what could be a semilattice polymorphism for this graph H? If you don't have an idea, look into the script. I think it's somewhere in the script. Where does the word polymorphism come from? Polymorphism. So that was Florian and me.
Polymorphism.
That's the same word in Italian.
Polymorphism.
Well, morphism, that's just because it's a morphism, like an automorphism or an endomorphism. Poly comes from a many, because of its many arguments.
Polymorphism.
Now already 4.
Polymorphism.
And again, twice as many in this way will beat Corona.